Welcome back to the 7th video about the full fly-by-wire electric outboard project. In the previous video we got our current measurement circuitry up and running and wrote some basic code for it. We have yet to connect the motor itself. Currently the current sensor is shorted out and fed clean DC from my lab power supply up to 5 amps. However, while accuracy was okay, well, noise was a little bit high for my taste. Card here, link in the description. So in this video we will try to reduce the noise. First, by maybe introducing some more hardware filtering at the input of our analog to digital converter, and secondly, of course, by introducing some software filtering. Enjoy! So, why do I think that additional filtering at the input of our analog to digital converter might improve things? We already have here an RC low pass with a cutoff frequency of 21 Hz and a rather large ceramic capacitor of 4.7 microfarads. And exactly that's the problem. It's a rather large capacitor. You see, when you buy a capacitor, they not only sell you a capacitance, they also put some toxic waste into the package. First of all, you have a leakage resistance, which slowly but surely will discharge your capacitor. Then you have an equivalent serial resistance, and finally an equivalent serial inductance. If we put all that garbage into an RC filter, then at higher frequencies, especially the equivalent serial inductance will start to block the current, and some of the high frequency will be able to pass through unfiltered. As a rule of thumb, the larger the capacitance of a capacitor of a certain technology or series, the larger the equivalent series resistance and the equivalent series inductance. Of course, I simplified things here to a fault, but you could fill a whole video with that topic, and I think EEVblog already did one. So have a look there. Anyway, that's the reason why, for example, in the MCP 3204 datasheet, see the basics for this family of analog to digital converters, a card here, link in the description. They recommend to put a 1 microfarad ceramic in parallel with a 100 nano ceramic to filter the supply voltage. The 100 nano, of course, having a lower equivalent series inductance than the 1 micro. And I propose we do exactly the same in our RC filter and see what happens. So currently we have that single 4.7 microfarad capacitor at the input of our analog to digital converter. Now I've added the 100 nanofarad capacitor. The 4.7 micro is now here. Please note that I placed the 100 nano as close as possible to the input pin to keep the inductances as low as possible. I did the same here for the pair of filter capacitors that filter the supply voltage for the chip. To determine if that additional filter capacitor actually is doing something, we have to change our code too. And we're no longer printing out the current in amps, but instead, again, we're printing out the raw binary value from the ADC, so we can actually see how much noise in LSBs we are getting. So power supply output is off, so we are measuring 0 amps, and if I stop auto scroll here, then the lowest value I see is 87. Do I get 86? Yeah, I do get 86. Wow. And the largest value is 3292. Do I... Oh, I get 94. Wow. Anyway, let's switch the output to 5 amps and see what we're getting now. Stop auto scroll. So smallest value 3369. Do I get a 68? No. Largest value 77. Do I get a 78? No. Okay. Now, in the previous video, we measured at 0 amps a noise of 5 LSBs. Yeah, I made a mistake there in the previous video, or 300 milliamps. And at 5 amps, we measured 6 LSB noise. Made the same mistake here, so 360 milliamps. With the additional 100 nano filter capacitor, we measured at 0 amps values between 3286 and 3295. So 8 LSB noise or 480 milliamps. And at 5 amps, we had values between 3369 and 77. Again, 8 LSB noise, 480 milliamps. That is, our additional 100 nano filter capacitor made things worse, and we can learn 2 things from that. First, we are obviously not handling here high frequency noise that is somehow blocked by the equivalent series inductance of our 4.7 microfarad capacitor. And second, the additional leads we introduced on our breadboards are obviously catching more ambient noise than we had in the previous setup. Yeah, quite a disappointment. But on a positive note, our 0 point only shifted half an LSB. And our 5 amp point only shifted 1 LSB. So that seems to be quite stable, and that's good. Now let's move on to software filtering. And for that we of course need to extend our code, and we will put the filtering into our current .h file, respectively into our current class, where our constructor gets an additional argument, a filter, which is by default 0, being no filter. And a filter is initializing a private member variable filter, also of the type unsigned integer 8. Beside that new unsigned integer 8 member variable filter, we have 3 more new private member variables. First, an unsigned integer 32 sample sum, and then an unsigned integer 16 sample num, and finally a float value. In the begin method, we initialize a sample sum, a sample num, and value all to 0. We could, in theory, do that in the constructor. We have a new method, a sample, which takes a reading from our ADC and adds it to the sample sum. And at the same time, it increases a sample num by 1. Now, if a sample num gets greater than our filter setting, then we calculate a value simply by dividing the sample sum by the sample num as a float, Yeah, I know. That's float division. Subtracting our ADC 0, and then we take the whole thing and multiply it with our ADC scale. Please note, if filter is 0, we take exactly one sample and then calculate the value, and it would have exactly the same value as before. After that, we reset a sample sum and a sample num to 0. And if we have not reached with our sample number the filter setting, we just do nothing. Our get method now just returns the value. So in effect, we take a number of sample until we can calculate a value, and that's it. So it's not quite a moving average. It's just averaging up or oversampling a number of samples according to the filter settings. In our sketch, we have a new constant, also unsigned integer 8, a current filter, at the moment set to 4, meaning we will average over 5 samples. When we create our current object, we pass now that constant as third parameter, setting the filter. In the loop, we call current sample each time we go through the loop, not only each 100 milliseconds. And I'm printing here out now current get again, but this time with 2 digits after the decimal point. Some remarks about the timings here. Our ADC is able to provide more than 80,000 samples per second, just looking at the time an SPI transaction takes. So about 8,000 samples per 100 milliseconds. So even with all the code overhead, we should get a fresh value here at current get every time we enter that block. And now let's have a look at the serial monitor. And of course, I removed the 100 nanofarad capacitor and put the 4.7 microfarad capacitor back into its original position. And here's the result on the serial monitor. Our power supply is off. We're really just interested in the noise level and how much we can get it down. So here are the numbers for filter setting 4, 5 samples. And the smallest value we get is minus 0.24. And the largest value we get is minus 0.13. Yeah, minus 0.13. Now, to speed things up, I will now change the code offline and set a filter setting of 9, so 10 samples, and then I show you the result. And then we go from there. That's the result for 10 samples. So the largest number is minus 0.24. Minus 0.24. And the smallest number is minus 0.38. Yeah, minus 0.38. 20 samples, smallest number, minus 0.35, yeah, 0.35, largest number, minus 0.27, yeah, minus 0.27. 50 samples, smallest number, minus 0.28, largest number 0.28, smallest number minus 0.33, 0.33. Okay. And just so that we have a baseline, I should have done that in the beginning, here with filter setting 0. So just taking one sample and printing it out. So the smallest value, minus 0.39. Do I get something smaller? No. Largest value, 0.15. Yep. Now let's have a look at the numbers. Let's go over the numbers. Just a short remark. What we just did was basically oversampling. That is, we took more than one sample to calculate our values as an average of these samples. So these were the numbers of samples we did, and these were the values we got. The minimum value and the maximum value, and I won't read them all out. From these, we can calculate the peak-to-peak noise by simply subtracting the minimum number from the maximum number. And as you can see, the noise decreased dramatically, though not as fast as we increased the number of samples. If we express the noise in percent, the value for one sample being 100%, it becomes even clearer. Now, the theoretical signal-to-noise ratio improvement you can expect with oversampling is the square root of the numbers of samples you take. To get that into our percent scale, we simply take 1 over the number of samples we took. And as you can see, the numbers roughly match up. Remember, in each case, we just looked at a few dozen values and took the minimum and the maximum value. So these numbers here for the peak-to-peak noise and the noise in percent are really bad statistic. But anyway, it's working. And that's not a given, because oversampling only works if the noise is really uncorrelated and random. Just as a sanity check, I have here the average of the min and max values, so basically the center value. And as you can see, as we increase the number of samples, we are homing into a value of 0.31, 0.305. While with 1 and 5 samples, we are quite off that value. That's another indication that this was bad statistics. But anyway. What's really annoying is that our zero value really drifted from the zero value we got last time when we did our amp readings. I don't believe it's temperature drift. At least I hope it's not. The ambient temperature today is about 2 degrees lower than last time. Celsius, that is. Instead, I believe that the fumbling around here on the breadboard changed some contact resistances, and since our voltage divider is relatively low impedance in the kilo ohm range, that can make a difference. Yeah, the joys of a breadboard setup. So let's calibrate that thing again. And let's do it properly this time. So I basically extended my loop by the oversampling mechanism we have in our current class. So I have here the two integers, a sample sum and sample num. They are of course static in the loop, initialized with 0. Here, instead of doing a current sample, I increase the sample num by a monitor ADC read of our current channel, and I also increase here the sample num by 1. And finally, every 100 milliseconds, I print out the average of our samples with 3 digits after the decimal point. And in theory, that average, the more samples we take, should converge to a value. And then we really have a stable 0 point, respectively a stable 5 amp point. Okay, let's open the serial monitor and see what we got. So 332846, 45, 46, 46, 45. Let's stop that. Yeah, we can let it run, but it's 45. Oh, it's stabilizing. 455, 456, 457, 455, 454. Okay, I think we can agree there's still a little bit of change here, but we are at between 3328, 454, 455, and 456. And there I see a 457. I guess 455 will be good enough for our purposes. And now we do the same for 5 amps. So, serial monitor, here we are. And we are at 3416. This is quite stable. 47, 48. We're still at 5 amps. 48, 487, 488. Okay, I think it has stabilized. So 3416, 486, 5, 7. Okay, let's say 486. Okay, now we just have to adjust our constants in the current class. So our new ADC 0 is 3328.455. And our ADC scale we calibrated by 5 amps. So 5 amps divided by that 3416.487 minus our ADC 0. And we let the compiler do the calculating. In the loop, I of course reverted the code again, so we are now doing, every time we enter the loop, a current sample, and every 100 milliseconds we print out again the current get with 2 digits after the decimal point. Let's have a look. So we are at 0 amps and we're getting here something between smallest number minus 0.15, okay, and largest number 0.2. That's a little bit disappointing, but it is what it is. Let's take a second sample a little bit later. Maybe there are just some spikes. So smallest value minus 0.16, largest value 1.6. Okay, and now let's go up to 5 amps. So smallest value 4.92. Yep. Largest value 56, 508, 511. Yeah, 511. Okay, let's have a look at the numbers then. Again, we are comparing our amp readings with 50 times oversampling to our amp readings from the previous video. Please note that 1-digit noise in the previous video with just 1 digit after the decimal point is equivalent to 10 digits noise with our 50 times oversampling, because we do have 2 digits after the decimal point. Anyway, for 0 amps we have an interesting result. So the noise level, I'm just going for the milliamps because they are comparable, is slightly higher than last time, but only slightly. I would have expected it to go down now. However, if we look at the average values and the delta to the actual current flowing, which is of course 0 amps, then we see a vast improvement. We had here a delta of 0.15, and in our first 0 amp sample we had 0.025, respectively 0.000 amps error. So that's good, but yeah, I don't really know what's going on here with the noise around 0 amps. Now at 5 amps we see what we expect. So our 5 digits, or respectively 50 digits noise, 500 milliamp noise, went down to 20 digits, 200 milliamps, so less than half. Our center value is now at 5.010 amps, so we only have now a delta of 0.010 amps instead of 0.05 amps. And yeah, that's really good, especially when you take into consideration that the dynamic range we have on our ADC between 0 amps and 5 amps is about 88 lsbs. So oversampling really works. In terms of a digital multimeter, if we say our measurement range is 0 to 50.0 amps, so we round the last digit off, then we would have a digital multimeter 500 count with a precision plus minus 1 digit. Again, that's very good, and it's much better than the initial goal I had of a precision of 500 milliamps. But if we can really get that, that's great. That's it for today. In the next video we will actually connect our motor and tackle the next challenges that await us. Till then, bye.